limit is nope. trying to think of the reason why. This must be x1. Why, Clement? Can kind of see it here. So we have R0 is less than 0 and R1 is larger than 0. And well, R2 is larger than 0 because X min is larger than 0. So typically you would have something like R0 very small and something like this. So the ordering that we talk about, ordering of D, is R0 is closest to 0 and then R1 and then R2. And this dotted line is X max, this is X min. The green or R1 is in between X max and X min. And we're talking about, well, I'm saying that if both are larger than 0, well, this one is larger than that one, so if this one is larger than 0, then the ordering will always be red, green, blue. I mean, doesn't matter where you put that thing. It's just this is the order. However, it is possible that this dotted line is less than 0, but of course not if the dot is here. If red is here, then this dotted line is larger than 0 because R0 is larger than 0. So for a start we have to make R0 negative. Let's say I put it on -2 or something. And yeah, it doesn't really make sense to change R2, I decided, because I think, yeah, I don't know, it feels like a scaling thing. Might as well just set that always to +10 and then do all the analysis. So I'm only going to change R1. And then you see that the X max here shifts, and well, as long as it is larger than 0, we know that the order is red, green, blue. But it's still red, green, blue for this value. And now it's negative. So I want to know what is the largest ratio between maximum ratio, actually the smallest ratio. Per definition, this is less than this in absolute value. That's why it's so red, because it is closer to 0 than that one. Now, if I put the green one must be positive, because we are looking for the case where the ordering is still this. Yeah, I can't do this, because now we're not even talking about that ordering anymore. I want to only talk about ordering D. And it turns out that the ordering D, thus red, green, blue, happens with an X max value that is less than 0. But in this case, they have the same absolute value. I just moved green as far as it could to the left until it ran into the absolute value of red. So you can't move it further, because then the color would swap to begin with. I mean, I can do that, but then I have to make I have to explicitly put red at the positive value and then the green at the negative value. I mean, if we're going to put this one at that and this one at that value. And now I swapped the red and green, yeah, and now I can make it smaller, yeah, but This is not what we were talking about. So I put this at minus that and this at plus that. So this is as far as it goes, green. And then it's, and it has a negative value, and the ordering is like this. However, clearly, well, the distance between, I mean, we are just moving, we're just changing R1 here. So I can make this value smaller by making the absolute value of R1 larger. And if we do that, then X max shifts to the right, because this shifts to the right and that one shifts to the right, even though it's not exactly in the middle. Therefore, the smallest ratio happens at the moment that R1 equals to X1, which is defined as the point of the value of R1 where X max becomes 0. So now the dotted line is at 0. X max is precisely at 0. If we make it even larger, then it's no longer the case that X max is less than 0, and that's what I am interested in. This, if now it's positive, I just know that this is the order. But if I do it like this, and maybe a tiny little bit less, so it is negative, then that happens for this ratio. And now the ratio, this distance divided by that distance, is the smallest possible. And that happens at, well, R1 equals X1. But yeah, that's why I started with typing divided by X1. But it's not that trivial now, I feel, to prove that mathematically. Oh, fuck proof. It just is the case, so I'm gonna type in X here. No, okay. Well, yeah, damn it. Let's put it this way, because X1 is the largest value. Yeah, we have to fulfill that. That's the reason, I guess. So now I can fill it in. Yeah, I couldn't find a good much less than. Just doesn't display very well. What we needed anyway. And this looks good. This is what I want. But then you copy it. And I paste it here and it looks horrible. What the fuck? Looks like a mistake. There's an enormous amount of space here, or what is happening? Yeah. No, I should put a space there all by itself. So what I'm saying is that even if the ordering is this and this is negative, then the distance from here to there and from here to there is more or less equal anyway. So I don't really care anymore about the color as long as it's either red or green. So this is red, green, and this is red, green, one way or the other. And if I'm mistaken, then I'm mistaken. I don't really mind or care. So we can pick an algorithm that finds this zero, or we can pick an algorithm that finds this zero. Both will be equally accurate. In the case that the ordering is this. Because, of course, it's also possible that this thing is negative, but they are not comparable. But in that case, they are actually inversed. So maybe I should always assume that they are inversed, if you get what I mean. So even in this case, I should assume that this one is green and that one is red. So we should go for this one. So I try to shift this one even further, and then green actually comes on that side. It is positive. See, now it's negative, but it is significantly more negative. And the order really changed. Now it might be important to actually find this one because, well, it could be very close to zero. And I want to find the one that is close to zero. So I think we have a good argument here to say that if x max is less than zero and x min is larger than zero, we should just always go for the point in the middle. Because even if the ordering is the other way around, then still that is the best option. And that argument then would fail, if this is not true. But in that case, they are all comparable. If the distance from 0 to red is comparable to the distance from red to blue, yeah, then they are all equal. So then it really doesn't matter which one I pick. So when it matters, which is in this case, it's best to go for the middle root. As soon as x max is less than 0. Okay, this is what I figured out while going for a walk. I think this is a solution. No longer fret about the actual order, but more about using this as a good heuristic for deciding which route we are going to calculate. Okay. So what is the consequence of that? I guess I have to calculate the sign of x max and x min. And then if they're both positive, we pick this one. If they're both negative, we pick this one. And if they're left and right, we pick the one in the middle. And the consequence is then that maybe we are calculating a route that is not the closest to 0. But then to see how bad that is, I could calculate the ratio between the ratio of the absolute value of the route that we're calculating over the absolute value of the actual smallest route. Let me put that in words here. Good. So I'm going to change this program again. Let's see, I'm currently we are now just case A, 100 million cubics. I'm going to assume that this generates nice random cubics still. No, it doesn't. So this is between 1/10,000th and 10, and this is also between 1/10,000th, but not larger than the absolute value of R2. And then this must be the same thing, just 0. Yeah. And then they assign arbitrary signs, and we call roots. Okay, so from the roots, then we calculate the coefficients of the cubic. And from there we calculate x max and x min. And I'm now no longer concerned with the actual ordering, so I'm going to delete all of this. Or that it's just failure. No. What am I doing? Its power of 2 returns false for 0. I mean, 0? 0 power of 2? Nah, not really. It doesn't even say this. Okay, so if n... Oh yeah, it's specifically added here. Otherwise it would not have worked. So I guess if n is 0, then this is false, therefore it returns false. So there must be a bit set. Exactly 1 bit must be set. So this should never happen. Huh? Could even kick that one out. Must be either R0 or R1. Let's talk about an error. So I'm gonna divide it by R0, I think. So if we pick R0, then that's gonna be 1. We don't have to do anything. Only when m equals 2, you can set the ratio to something else, namely the absolute value of R1 divided by the absolute value of R0. Probably doing a nonsensical thing, so in this case I know the ordering, so it's just going to be R0 all the time. Yeah, or it's just always that one. Might well be paranoid-ish. I mean, by removing this, I kind of fill in something that is not necessarily true if I am extremely mistaken. So I just stupidly test all of them. We want to the root that is less than x max. So I'm testing if this is less than x max, set a bit. If R1 is less than x max, we set a bit. This way we pick one, and I'm saying that, well, it should always be R0 actually. And the other ones therefore not. It can only be one less than x max. And then of course we don't have to do this, the ratio is just 1. R0 divided by R0. Okay, so in this case we want to do that one. And here I can also predict that this is going to be the correct one, namely R0. I think. And in this case, oh. Yeah, okay, just this. So larger than x max. And less than x min. I should do it the other way around. Where's 0? Yeah. And in that case, it is going to be equal 1, or it's going to be equal to 2. And then if it is equal to 2, then we have a different ratio. And I wanted that to be larger than 1. So 1 divided by 0. And then I want to determine the worst case scenario. So if it gets larger than the worst case, let's start at 0. If ratio is worse than the worst case, and let's just print for when that happens. Can I go back? How far can we go back? Yeah, this is how I printed it. So I have a column at the front, which is the actual ordering. Yeah, well, I don't have that anymore. I forget to print the worst case though. Two. Well, manageable. Yeah, of course, manageable. So in the absolute worst case, it's only a factor 2 larger than the actual minimum root. But yeah, nothing. I mean, it's only a problem when it is 1,000 or maybe 10, but 2, it's literally a single bit. So I'm totally going for this. It might be interesting to display how that looks like. So we do have -2, 4, 4. So these two are just equal, and the other one is half that on the other side. That would be cubic root 2, I think. Okay, so is this one, for example, 2, and then this one to minus. For the what? -4. And this one also to -4. So, like that. It was the other way around, but okay. So yeah, this is now exactly on top of it. This one is -4, which means that this one should be positive. So we can change this a little bit. Now it's positive. You can also see the separation here. Because now one is negative and the other one is positive, we are going for the green one. It's in the middle of these two. While that one is not the closest to 0. This one is. But the difference is only a factor 2, just a factor 2 further away. On the other hand, the derivative in this point is almost 0. You don't want to do that. I should go with this one. Otherwise my Haley won't work very well. guess the worst case scenario is if you combine something that is close to 0 with having a derivative of 0. So if these two are almost on top of each other, and then yeah, it doesn't matter which one you pick, they're both close to 0, but the derivative is 0 as well. So it's still going to be pretty hard to calculate. You know what? Maybe. No, it's always going to be that one. I thought I'm going to go for the one with the steepest slope, because then the Haley algorithm works the best. But that would be always the one that is not in the middle, aka this one in this case. So then I would like that, because it is it's the one that's closest to 0 anyway. So the question is now, when do we really want the one in the middle? Well, we want that in the middle when it is significantly closer to 0, despite the slope. Slope is also hardly different in this case. It's a steep slope. The slope is more or less the same. This one is a little bit steeper, but not even much. So in this case, it's way more important that this one is close to 0. So it is a good thing to go for the one in the middle if these things have different sign. Except in that one case, right? When this one approaches that one. That's what we had eventually. That is more to do with the curvature. The curvature here is positive. So it's, as soon as this thing in the middle goes on the other side of the inflection point, it starts to become dubious. Maybe. So let's see. Maybe draw a line with the inflection point is 2. So just put it in here. Set this to something small, close to 0. I should always pick red here. But okay, red is close to green like this, but never close to the other. So this completely works. The algorithm completely works in this case. So both are negative, we pick this one. If both are positive, we also pick this one correctly. And then if this one is negative and this one is positive, then we also pick this one. And that is the red one, because, yeah, I mean, at the moment, well, not exactly. There is a point here where, indeed, but that's the whole negligible thing, right? So let's make this significantly bigger, then you can put it over here. So now this thing is still positive, therefore we calculate that one. But yeah, I mean, they are now almost indistinguishable. And as soon as you shift it even further, now it's both negative. Now we pick this one again. But it did go wrong if R1 and R2 are close together. Because, yeah, not in this case. Yeah, what? We put those two very close together. So I don't like it that the derivative is almost 0 here. But okay, both are negative, so now we would still calculate this one. And that goes wrong if this one is now moved away from the 0 until x min becomes positive. And of course, the slider doesn't go far enough. This one on did 8 work or also not? This should work. Yeah. So now it's x min is larger than 0. And this one is less than 0, therefore we would calculate green with the current heuristics. Then that's not good, because the derivative here is just way too bad. I should pick this one. So now, to find out when to change the heuristic. So this is bad. I don't want it. And it has to do with these two being almost equal, I think. If that's not the case, then yeah, now the derivative is comparable, right? So it's especially problematic when these two are almost equal. Then, is there anything I can do here? Nope. It's just this little range here it's going wrong. But that's because I'm at the end of the slider. Damn it. I want to not be bothered by that. Well, I can only go to 4 here. Bah, let's just change it. Two. Okay, minus 10, almost minus 10. And then this one must be positive. So from here all the way up is we picked the wrong one. How can I detect that I don't want to use this one? So not just because it's on the wrong side of the inflection point. It's always between red and green. So I know these two are, or do I know that? Okay. What the hell? Okay, inflection point. Probably a better way to calculate this. But well. Why not like that? Now I have those values anyway. Yeah, so I would like to draw an evaluation actually at that point as well. That inflection point, let me just use the formula. I think it is something like minus one coefficient divided by another coefficient. I used to know that from my head, but no. Inflection something. Two, yeah. Yeah, so this is the one. Yeah, this is C2, I think. I have C2, right? Yeah, C2. And the other one is C3, which is 1. So I just have to divide by 3. Let's call this also X. Yeah. Mm. I don't know. Pick another color. 13. So we'd say that in this case, because evaluation at the inflection point is less than 0, we should pick red. Actually, pick red anyway. I have to bring this one to the other side first. Like this. Now this is super negative, therefore we still should use red instead of green, because this one is positive and that one is negative. And then if you change the green point until the inflection point, boing, what the hell happened? Becomes positive. Yeah, now we pick the one in the middle, which is red again. Yeah. You can cross it. Let's see, yeah, but now it's again smaller than... Gee. Can't cross it even. Wow, this is the best detection ever. This is what I have been looking for. Or not. Suddenly, how did I do that? Oh, they're at the same distance now. And a minute. Yeah. Okay. We can cross it here. So in this case, that one is positive, that one is negative. So the current heuristic says use green. And I will use green because this one is positive. But that's okay. Even though this one is closer to the 0. That one is comparable. But if you shift it like this, now we pick red anyway, even though this is positive and that is negative. Because now the evaluation at the inflection point is negative. Don't want to use this anymore. Especially not if, well, you know, because of this. But why not already? Because in the end we want to use red. So now I can add to this program that heuristic and then draw a little circle around the route that we will calculate first. So you see immediately which route will be calculated first. And in fact I have a little trouble seeing where my x equals 0 is. So maybe we should draw a black line here as well of some color. For the axis. Both axes. I want to see both axes. Well, they don't change, so I might as well draw them here. Layer line style line constructor arguments. Yeah, I did that. Point in the left. Need a style though here. A solid line style. A solid line style and maybe change the color a little bit. Yeah, I don't know. Something pretty dark. Dark gray. You call this dark? It's not dark at all. This is dim gray. This one maybe. I have a lot of colors, but I can't find the dark gray. Slate gray. What else did I want to do? What? It's me. What is this about? Layer. That should be good. Background layer is existing. Auto. Create background layer returns a boost intrusive pointer to a layer type. Okay, then the line style, solid line style. That's a line style, tall line style. Followed by arguments. Oh, it's because it, of course, doesn't know this type here. Yeah. Should use a different color, I guess, for when this is negative, positive or negative, and that one as well. Gotta search again. Violet. Why not? So, we need something for x. What x max is negative, and then one for this positive. choose this one for positive. T. No, not visible. Must be much darker. That one is reasonable visible. What's the other one? Make the other one reddish, maybe. I don't know. Fuck. What? It's not the one that I want. Yeah. It must be a circle style. What's the position? Nobody knows. Circle, yeah, position. Center radius. I have no clue what the radius would be. Maybe this is 10, right? 0.1. Maybe more. Let's try this first. And this is then at root, comma cubic root. Yeah, what? Yeah, it's drawing an ellipse, which is completely flat because this thing is way higher. In fact, 10 times. So I need to draw an ellipse that is higher than wide. And even that doesn't look good. At center is not the right thing then. Really weird. Let's make it twice as big. So 4. Can I define the radius of an ellipse? I mean, I think we have only one radius here. Do not have an ellipse. God. Okay. Let me think about this. To fix it, or draw a rectangle instead, or add an ellipse. Guess. I mean, if the ratio of the graph is not equal, then x and y is not correlated, usually, and a circle is not a circle. So really I should not draw a circle, but I should draw a shape. I have a circle as a shape, but I can't change the radius of that, which is maybe the problem here. I'm gonna draw something else. Connector. I think you can pass a line style to connector style. Try that one. And then how to create a connector. It's just 2 points, from and to. But no pixels. Would have been nice if we could pass pixels. I think the whole thing is kind of incomplete sometimes. can 5 be too much? Yeah. An arrow pointing to the root that is being picked. How about that? If it points to red, then we're always happy. And it points to red because these colors are the same. So not interested in that case. I'm more interested in these cases where these colors are different, aka left and right of x equals 0. Still pointing to red. Yay, what a success. Okay, well, we can move this one. That is always pointing to red, man. This one, this one. So good. Except that it is a little bit too good. No, it's not too good. It's still doing the right thing. I'm gonna demolish it. Oh, no. Yes, now it points to green. And it's doing the wrong thing. No, it's doing the right thing. But you have to fix this. Okay, so definitely pointing to green here. Good. Okay, so if at the inflection point the evaluation of the curve is negative, that means that because this slope is always negative, so this green dot must be on the left. So if this is negative, you simply must not pick this one. Only pick it if this is positive, aka in this situation. Or not. Nope. Oh, wait a minute. Now it's pointing there again, but it's here. Yeah. This is not going correct. This is not good. Okay, so the sign depends on something, namely yeah. What? Why? What is the correct heuristic? That thing is larger than. You don't want to be. We don't want to point here because it's. Because it's on this side. Why do I not want to use this side? Because the whole curve is, the whole curve is higher than, because the inflection point is higher than, the inflection point is a positive y, I don't want to use this side of the curve. Is that correct way to say it? But no, it has to do with the sign of the x inflection as well. Because it's a side that is further away from x is 0. That's why I don't want to use it. Is that true? Maybe. So in the other case, I think we saw that only when this is on this side. And then, let's say, I want that in the middle. And now I need this to be positive. And then we need this to be positive. But we don't get that there. It's not that is not positive anymore. I can also do this. Yeah, now we are here. So yeah, this is the side. The side that is the closest to 0. That is the side that we do want to use. Don't want to use the side that is away from 0. So we just use this, but not this, because now it's on the wrong side. This side is further away from X. And why is that case? That is only the case, obviously, because the inflection X is negative. So that the sign of X inflection toggles it as well. So it is not that I don't want to use a negative Y inflection. I don't want to use when the sign of the Y inflection equals the sign of the X inflection. Let's use that. So the sign of the Y inflection must be unequal to the sign of the X inflection. And then we can use that other route. Yep, now it works. So we can use this green one, but not this green one. Closer to 0, oops. Closer to 0, not closer to 0. And then it should now also work if this one is positive. Yep, so we use green until it goes beyond the inflection point. Then we switch to red. Okay, I think this will do. Yep, except that I have been cheating. I'm just assigning here R1 and R0. What they really mean, of course, is that we are going to look for the root that is on this or that side. And I did check it with a search that that is R0. But I'm not feeling 100% certain about that anymore. So let's add a search back here. If x max is let's say is x max is larger than 0, then we wanted to use this one. Yeah, so I can't pick R0. R0 is defined as the root that has the smallest absolute value. But until I calculated all of them, I don't know that. But we can go for the root that is on the left of x max. And it should be the case that if this is larger than 0, that is R0. So I can just now assign it, but still, yeah, to check that, then of course this holds. So yes, R0 is the one that is less than x max, and the other ones are not less than x max. And then we have thing in the middle. I'm gonna do it this one first. And again, this should be. Why is this assigned here? Wait a minute. Double root declared, I mean. So this should be R0 again, which when we can check as indeed larger than x min. So R0 must be the one, the only one that is larger than x min. And in fact, I tried hard to never get even in the neighborhood of a local extreme. So I don't think when they are equal, then the derivative is 0. I really want to avoid that. So let's remove the equal signs. Oh, actually, those can be equal. This should not be equal. And this line is not used, but I'm going to use it now, because this just figures out brute force, basically, which one it is that is in between x max and x min. And then again, he must have the assertion that there is only one of them. It's either R0 or R1. Just so difficult. So if this is the case, then R1 is the one that is in the middle, which would be that one, therefore we assign it. And then I don't have to do a search actually, because, well, we just figured it out from here. All those tests have already been done. But yeah, if this is the case, if this is equal, then we don't want to do it. Then where are we going for then? That must be then either this one or that one again. So this is the exception, right? So let's first do it like this. If it is equal to that, exception. Yeah, well, in that case we have to end up with R0 again, but how? How? How to get root 0 here? What? What? How is that possible? How is that possible? Well, it would be only possible if a root is not updated. You just get stuck at... Yeah, just stuck at the same value. Undefined behavior. Yeah, okay, so root, it's not set here, it's not set here, so this is true, and then this is not true. And this is also not true, then it doesn't get set. Yeah, so rather it's either equal to 1, which means that R0 is in between, or it is equal to 2, because it is a power of 2 and it's not 4. It's just asserted directly. It's either that or that. Not for. I mean, yeah, then it is not for the. And then we can do simply an if else. The other way around, actually. Yep. I guess it's 0 in that case, because they are equal. Yeah, doesn't really matter, I think. Equal, no, actually. Those pesky equal signs. Okay, how about just do that here. If you're overriding it anyway, then I don't care what the result is. This should be overridden in that case. I think. Nope. You see, R0 and R1 are both equal to X min here. So true, false, because it's equal. And then this is true and false. M is 0, so root is not even set. And then I said, well, but then this should be true. But apparently not. You really have to pick then. Let's pick the worst one, as in R1. So if it is equal to X min, we just pick R1. Yeah. Because I would rather pick R0, but yeah, well, I mean, by picking the worst one, maybe I'm alerted to the fact that that's happened, as it were. What? Okay, time to run in debugger. And we have no mouse. Always fun. Yeah, that should not have happened because... Oops. I really wish I could move this. Is there a way to move a window with a keyboard? I missed the chat again. Who's the goops? Hi. Wave if you're still there. Or say something. Okay, I guess that the problem is that due to floating point round-off errors, we don't have a route that is in between xmin and xmax. But how the hell is that even possible? No. No, that should not be possible. So it just, yeah. Floating point round of errors. I forgot an else. No, else is here. But I suppose also that is possible. Yeah, seems to be fixed. It's pretty difficult to get that situation even. Yep, no, I got it. Yeah, they have to be more or less the same. No, just, yeah. More or less absolute. The absolute value should be more or less the same, but opposite signs, and then you can get this. No, it's not really the same, of course, but well, I can change this from 3, so now they are the same. And now they are not. I mean, they're just this crossing here. All while this dotted line is positive, on the right of this y-axis. Yeah, and the question is thus that if now I reject the green one because the inflection point becomes negative, so here, then why would I take this one and not that one? I suppose it's just the same direction as in towards x equals 0, not away from it. It's kind of obvious, right? Yeah. So try the other side. 3.46. Oh, it fucking crashed again. You gotta be kidding me. Why? It's again something that's almost the same. And again, I can't move my window. Nope. Okay. So almost same is also okay in this case. For those two. The two that have an equal sign. Almost equal x min. No, what did I do? So I made this positive and then that, okay. Wow. Yeah, yeah, okay. To almost equal is also possible here because we didn't do the other check yet. In the end, I don't want that, but at this point, it just can it can be also almost equal, even for that one. 160 quid, yes. Enter as well. Almost equal to min. Yeah, seems to work. Right, so here we have red, green, on green to be on. What the hell? Hold on. How do we do this? Green must be in the middle. One must be negative. Yep, like that. Okay. Yep. So we, in this case, we jump towards x is 0 and then well beyond it. From well, we just jumped the other way. Baha. So the one that we pick is simply depending on, again, then the sign of the x inflection, for example, or y inflection, doesn't really matter. Yep, yep, yep. And this completely overrules this, like completely. Yeah, I think so. So I can move it to the top then. Don't have to add it to this block as an exception. Now let's call this 0 and this 1. And this 2 and this 3. So if the inflection quadrant is 0, that means that this is not true and this is not true, which means that the x inflection is larger than 0 and y inflection is larger than 0, which means that they have the same sign. So this is true. And then we would do normally, if x inflection is less than 0, then we do the root that is larger than x min. Wait a minute. This talk, yeah, here. The root is this one. If the x inflection point is less than 0, so that would be quadrant 3. And then quadrant 0 is the other one. Okay, does this crash? Please don't crash. It crashes. I should have moved the window, I guess. Quit. Let's try it out here. Oh. Oh yeah, this assert holds for that test. It doesn't hold for this test. Ugh, getting tired. Yeah, then maybe I should treat them separately. I'm not doing anything special here except assert that this root is indeed the one that matches that, or matches this description, the root that is larger than x min. Did I delete the other comments? I'm afraid I might have. Yep, I deleted it. Damn it. I'm going to separate them. Actually, maybe it should have worked, so I don't really get it. Let's draw an arrow at R2 in these cases so I can see when this happens. Yeah, wait a minute. That's no. What? Okay. Likely. It just doesn't make any sense to put it there. I should put it here. Well, it's even wrong here. One, two, three, four, five, six, 7, 8, 9, 10th digit instead of 12th. Whatever. Whatever. How the hell do you write prevent? I do get the impression that we are really testing it though, because I've heard it absolute every possible problem. Now what? Yeah, don't tell me that this is even worse than 9 digits. Come on. No way. Our 0 is very small and X marks is... That's not equal. Okay, I had it for today, really. Let's play some chess. After killing this thing. See my rating. Holy shit, man. I raised completely back to top strength. Don't ask me how I did that. I was like, what? I dropped till 1800. 1800. I didn't understand it at all, really. Maybe it's because now I put my bishop outside of the chain. Aha. Okay, double attack here, attack there. Well, could go here. Don't see a problem with that. Defend this. Stop defending that. That's actually a problem. This one is defended already. It's just this has to be defended. Why not push it? Or let him take it? Nah. Thinking about this move, queen here. He takes. I take back and I just have double pawns. So therefore he probably takes here first and he wins a pawn. And then I take the queen and then he takes with check and I take like this away from the center. And then he takes my queen. And then I put my bishop here, trying to win this one back. Now maybe he plays the knight over here to defend it, because the rook can't go here because the bishop attacks that. And then we put the bishop here, pinning the knight. I'm going to win it back, but yeah, I have a double pawn here. It's not good, is it? Just play this. I ain't going well. Man, that is going bad. possibly bad. I don't have time left. Hello. Yeah, saw that one coming. Oh, I did not see that it was defended. Damn. Is that a problem? Yeah, there's a problem, because now this square is attacked again. No, I don't have time, so let's just watch this be lost. Not a bad move. No. Damn it. Yeah, okay. Time to give up? No, resign. My God, what was that? What happened? The bishop is not good. Okay, to remember that. But it wasn't a complete disaster yet. Just half a point. Yeah, yeah. That's so the only reason I didn't play my bishop back is because it came from here. You just mentally refuse to do that. Although it seemed to be the most logical move, I have to admit. I mean, this is defended, I have to defend that. Queen is occupied, can't defend it with a knight, so it's either moving this pawn or losing the pawn or moving the bishop back. All the other moves should be giving, well, knight c6 is apparently possible-ish. Although I wouldn't know why. Yeah, I mean, it does drop a pawn. This isn't even mentioned, it's probably really bad. Plus 2.6, yeah. Can't do that. He did not play the best move here. Okay, this pawn would have been stopping that knight from coming in. And I try to castle, plus 2.8. 3.6 I mean. Just, no, it's 3.5. Yeah, it's already lost. Wow. So I should have played this, then give away this piece or something. Have to give it away anyway. Why is this a good move? Well, good. I mean, less worse. And now I can do this. Seriously? Oh, okay, that's why. This one stops the bishop from coming in. Mm. Yeah. Break here. King has to go there. I eat this pawn, then I eat this pawn and promote. In order to do that, we have to exchange all pawns. So start with taking here. And then walk with this one. And this one. Can't really calculate it, but let's try that. Take, take, push. Let's say king here. Push again. Has to take, take, take. Must go back in the square. So the king goes here instead then. Let's say take, take, push. King goes here. Push. I'll try to walk it. It's not much fun. Can it stop me? Goes here. And wait a minute, I'm attacking it. So he doesn't want to lose that pawn. So he could push it, but then I go here and then the king goes here. Wait a minute. Take, 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 ting, doing, doing, doing. I just leave it like that, I suppose. So then I can come in. Doesn't not have a free pawn then. Or he has to go take this one, and then walk. I'm probably faster. Well, or am I? Take, go here, push. Go forward. King, take. Take. I'm too slow. Way too slow. Still going to take here. But now. Maybe just push this pawn. So let's say push. If he pushes even faster, so he doesn't do that. This might be interesting though, because it does stop me from walking ever. Yeah, that's not good. So if I push this one and he pushes that one, then black has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 moves, and I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 moves. That's not good. So then I guess it's either the king or this pawn. I would say the pawn. Still the pawn. Pawn. King here. Now what? It threatens to go here, but then I push. And then it can't take. If it takes here, I do this. I must go there. And then I go here. H, there, G, there, F, E, D, B. B already? No. Well, that's the draw anyway. Damn it. So again, we do this. Goes there. And then goes there. I go here. Yeah, it goes here. Go here. Take. And I lost track with my king was. Yeah. Tok. Pok. My king is here. Pok. King here. Take. So 3 rows in between. So I take, and then he goes to G. I do not take. I go here, and he goes to G. Go here, he goes to F. I go here, he goes to E. Ah, plenty of time. And we don't even get a chance to play that out. What is the rating of the puzzle? The rating of this puzzle was 1964. Jesus, I had way more trouble than that. First thought is you give check here, but that would be too easy, wouldn't it? But it does win immediately. I mean, he can't take it. That would be... No, it's not mate. You can put something in front of it. Okay. If he puts the queen in front of it, then I give check here. Then the queen has to come again. It's mate. So he has to put a rook in front of it. And then I don't even have a check anymore. Well, actually I do. I can go here. And then you have to put either the queen or the rook in front of it. That's again costing material, isn't it? G check, take, queen, check. If the rook goes in between, I can give check here, and then he has to put the rook in between, otherwise I'm gonna take it anyway. Then I have one pawn more. No, and that's nonsense. The rook comes here. I don't have check. I just don't have check. What about this move here? Suppose he takes my queen, I take his queen with check and win a rook. I mean, with check he takes my rook. And then I win this rook, but this is not good enough. Maybe go here with queen. Yep. It's either this check or just go with here with the queen, I think. But if I would do this, I can just put the queen here, defend that square, threaten everything. No, I cannot, because I just take this. He has to defend this rook. I cannot defend this square. So the next move I can give check. And then the king comes here. And then I want to give check here. Or here. That would even be better maybe. Now to give check here. So he goes there. And then I can take the rook with check for free. That would be good. So he kind of would have to at least defend this square. But he can't because, well, not with this rook. Definitely not with this rook. And that wouldn't work really. I think this is the move. He sacrifices the rook. Why? And then you can go here with check. And then I go back. And then you can save this rook maybe. So if we go here, then he just gives also check, defending that, and then saves the rook. So I'll probably just take it. Now, that was a 2473 rated puzzle. Really? Blunder. Mate in 12. White is winning. Gotta be kidding me, right? And the draw. Wow, why? Yep, also a draw. Now this is a hard puzzle. I have absolutely no idea. No idea what to do. Try this one. Yeah, that wins apparently. Yeah, nobody knows why. Plays on that side. Why? Oh, wait a minute. That was a slight minor mistake. Okay, now even I can win this. Does not want to take my pawn. It does not want to take my... Now it wants to take my pawn. No, I don't know. Actually. Still not running into the 50 move rule. I made it. Fifty moves, so move 55. Promoted here. Promoted here. Take something. 63. So I did 42 moves. Okay.